Hi, welcome to the class of stochastic processes. Today we move on to chapter 5, which is the exponential distribution and the Poisson process. In fact, the exponential distribution is a very important building block of the Poisson process. So in this chapter, we will start with the introduction to exponential distribution, followed by the introduction to Poisson process. If x, a random variable x, is exponentially distributed with parameter lambda, then the density function f of x is equal to lambda exponential minus lambda x if x is greater or equal to 0. And equivalently, we can calculate the CDF of x, which by definition is fy dy. Then we take integration from negative infinity to x, which is 1 minus exponential minus lambda x. Of course, x has to be greater than or equal to 0. Then we can also calculate the expectation of x, which by definition is f of x dx, and we take integration from negative infinity to infinity. And that is x, and then this is f of x. Okay, so if we apply the technique of integration by parts, and then we can calculate that the expectation of x will be 1 over lambda. Moment generating function. By definition, moment generating function phi of x is equal to expectation of exponential tx, and then we can find that the result will be lambda over lambda minus t. Variance of x will be expectation of x squared minus expectation of x to the square. Okay, and expectation of x squared can be obtained by taking derivative of phi of t twice, and plugging t is 0. So that is 2 over lambda squared. So we put this expectation of x squared back in here. So variance of x will be 1 over lambda squared. Example. Suppose that you are receiving rewards at randomly changing rates continuously throughout time, and we let R of x denote the random rate at which you are receiving rewards at time x. So this x represents time, and R of x represents the random rate. So R of x is essentially random. Now we let the quantity R be exponential minus alpha x times Rx, and take integration from 0 to infinity dx. And this is actually called the total discounted rewards. So basically, if this is the time horizon, and this is time 0, and this is the time point you get the reward. If this is the time point you get the reward, if this is the time point you get the reward. And basically, this R is something is kind of like a quantity that you discount all the reward value to time 0. And then, because remember we say R is random, so we can take expectation of R. So E of R will be expectation of exponential minus alpha x R of x dx. Recall that x represents time, so x is not random. So if you take expectation here, basically you are taking expectation with respect to R. So you can just move the expectation inside the integration, so you will have the total discounted reward like this. Now we want to show that this total discounted reward is equal to expectation of R of x dx, but x is from 0 to t. Here t represents an exponential random variable with rate alpha. Now we see why this can happen. Solution. Now we define an indicator function I of x be 1 if this random variable x is less than or equal to t, and this indicator function is 0 if x is greater than t. So basically r of x take integration from 0 to t can be expressed as r of x times the indicator function I of x dx, because this I of x is 1 when x is less than or equal to t. So basically, when you take integration from 0 to infinity, you only have I of x from 0 to t, because I of x is equal to 1 whenever x is less than or equal to t. Now, the right-hand side expectation of Rx dx from 0 to t is equivalent to expectation of R of x Ix dx from 0 to infinity, because we have known that this integration is equal to this integration. Now we can move the expectation inside the integration. And because this R of x and I of x are actually independent, so this expectation of R of x times I of x can be separated as expectation of R of x times expectation of I of x. And basically the expectation of I of x is equal to probability of t greater than or equal to x, because expectation of I of x is equal to 1 times this probability t greater than or equal to x plus 0 times probability of t less than x, and this is simply 0, so you are left with this, right? So, and because this x and this t is actually an exponential random variable like this, because we have made sure t is an exponential random variable. So the probability that t is greater than or equal to x will be exponential to the minus alpha x. So in summary, we get the conclusion like what follows. So we show that the expected total discounted reward, which is the right-hand side, is actually equal to the expected total undiscounted reward earned by a random time that is exponentially distributed with a rate equal to the discount factor alpha. Properties of the exponential distribution. First, we talk about the memoryless property. If a random variable x is memoryless, then it has to satisfy this equality, which is the probability of x conditioned on x greater than t, the conditional probability that x greater than x plus t is actually equal to probability of x greater than x. So that means whether or not you know x is greater than t, it does not affect the distribution of x. And then we have actually two distributions that have the so-called memoryless property. One is the geometric distribution, and the other is exponential distribution. We'll prove that why these two distributions are memoryless. If x is geometric distribution with parameter p, then we know that the CDF of x is 1 minus p to the power of x. So actually the conditional probability of x greater than a and then x greater than a plus b is equal to probability of x greater than a is equal to, because f of x is x less than or equal to x. So x greater than x is simply 1 minus p, and you plug in a in here, right? A. And similarly, x greater than a plus b is equal to 1 minus p to the power of a plus b. So we get 1 minus p to the power b, and that is probability of x greater than b. So condition on x greater than a, and x random variable x is greater than extra b is equivalent to this probability without any conditioning. So that is so-called memoryless. And similarly, you can prove that when x is exponentially distributed, and you can prove that this conditional probability is equal to this probability without conditioning. So that is memoryless. Example, suppose that the amount of time one spends in the bank is exponentially distributed with mean 10 minutes. So lambda is 1 over 10. What is the probability that a customer will spend more than 15 minutes in the bank? And then what is the probability that a customer will spend more than 15 minutes in the bank, given that she is still in the bank after 10 minutes? So if we let x be the amount of time that the customer spends in the bank, so the first question actually refers to x greater than 15. So because x is exponentially distributed, so we know that this is exponential and minus 15 times lambda, and lambda is 1 over 10, right? So it turns out that this is exponential to the power of minus 3 over 2. And given that the second question is, given that the customer is in the bank for 10 minutes, what is the probability that the customer will spend more than 15 minutes? So after 10 minutes, the customer spent extra 5 minutes in the bank, right? And because exponential distribution is memoryless, so extra 5 minutes, we can simply calculate probability of x greater than 5. So that is exponential to the power of 1/2. Another example. So we consider a post office that is run by 2 clerks. Suppose that when Mr. Smith entered the system, he discovered that 2 customers are already in the post office, which are Mr. Brown and Mr. Jones. So suppose that Mr. Smith is told that his service will begin as soon as either Jones or Brown leaves. And if the amount of time that a clerk spends with the customer is exponentially distributed with mean 1 over lambda, then what is the probability that of the 3 customers, Mr. Smith is the last to leave the post office? So because we know that exponential distribution is memoryless, so remember that when Mr. Smith enters the system, Mr. Jones and Mr. Brown are being serviced. So, and then Mr. Smith will only be serviced only when Mr. Jones or Mr. Brown is finished their service. So when either of them finish their service, then Mr. Smith and Mr. Brown start basically because of the memoryless property. So Mr. Smith and Mr. Jones, or Mr. Smith and Mr. Brown, they kind of like have a refresh start. So Mr. Smith will leave the post office, will be the last to leave the post office, will have the probability of 1/2 because of the memoryless property. Example, the dollar's amount of damage involved in an automobile accident is an exponential random variable with mean 1,000. Of this, the insurance company only pays the amount exceeding the deductible amount of 400. Now we want to find the expected value and the standard deviation of the amount the insurance company pays per accident. So if we let X, random variable X, be the dollar amount of damage resulting from an accident, and Y is X minus 400 plus, that means only if X is more than 400, then the insurance company will kick in and pay the extra, right? So actually, this Y, the amount Y, represent the amount paid by the insurance company. So recall that X minus 400 plus means only if X is more than 400, and then Y is positive. So for example, if X is 500, Y is 100. If X is 300, Y is 0. So that's the notation of X minus 400 plus means. Now, we use the indicator function IB. If X is more than 400, I is equal to 1. If X is less than or equal to 400, I is equal to 0. Now we can calculate the expectation of Y given I is equal to 1. Remember, if I is equal to 1, that means X is more than 400. So, and also because X is the amount of damage involved is exponentially distributed, right? So X more than 400, based on the memoryless property, we know that this Y, the distribution of Y, is simply like the exponential distribution with parameter 1000. So expectation of Y is equal to 1000, just like X. And if I is equal to 0, that means X is less than 400, then expectation of Y is equal to 0. Because if the amount of damage involved in the accident is less than 400, the insurance company is not going to pay anything, right? And similarly, we can know that the variance of Y, if I is equal to 1, this is simply like the distribution of X. So the variance is like the variance of X, which is 10 to the power of 6. And similarly, variance of Y given I is equal to 0 is equal to 0. Now, the random variable I is basically Bernoulli distribution with parameter P equal exponential minus 0.4. So that means I will be 1 with probability exponential minus 0.4, or 0 with probability 1 minus exponential minus 0.4. So expectation of I is like this, and variance I is like this, P times 1 minus P, right? Recall that the Bernoulli distribution, if the parameter is P, the expectation is P, and the variance is P times 1 minus P, right? And why the expectation, and why the random variable I has Bernoulli P being exponential minus 0.4, because that is that if we look at this expression, we know that only when X greater than 400, I will be 1. And the probability of X is greater than 400 is equal to minus 400 divided by 1000. So that is E negative 0.4. Okay, so now we can go back and take a look at the expectation of Y. Expectation of Y is equal to expectation of Y given I. So that is actually 1000 to the expectation of I. So that is 1000 times exponential minus 0.4. And similarly, based on the equalities we have learned, in chapter 3, we know variance of Y is equals to this. And then if you compute the expectation of variance y given I, then that is the expectation of this. Then that is 1 to the power of 6 times expectation of I. Expectation of yi is actually exponential to the minus 0.4. So we have this. And similarly, variance of expectation of y given I is like this. So you can compute the expectation, the variance of this. And the 10Q can bring out the variance. So you have 10 to the power of 6. And the variance of I is equal to exponential minus 0.4 times 1 minus exponential minus 0.4. So, and because the question is actually asking for the standard deviation, so you simply need to take a square root. So we get about 944. Another example, a store must decide how much of a certain commodity to order so as to meet next month's demand, where that demand is assumed to have an exponential distribution with rate lambda. If the commodity costs the store C per pound and should be ordered so as to, if the commodity costs the store C per pound and it can be sold at a price of S greater than C per pound, how much should be ordered so as to maximize the store's expected profit? Assume that any inventory left over at the end of the month is worthless, and that there is no penalty if the store cannot meet all the demand. Now, we let X be the demand, and remember the demand is assumed to have an exponential distribution with rate lambda. So X is an exponential random variable. And T is the order quantity. So basically in this problem, we are going to solve for T. So T is the decision variable. Now the profit P can be written as S. That is the price you sell your product, commodity, per pound, right? So S times minimum XT. Why we put it minimum XT? Because T is your order quantity and X is the demand. And we can only sell the commodity at the quantity of minimum XT, right? And minus CT. So CT is basically your cost. And recall that minimum XT, there is an equality like this. Minimum XT can be written as X minus T plus. Now we first look at this, X minus T plus. So expectation of X minus T plus, we can divide it by two cases. Divide it into two cases. First, X greater than T or X less than or equal to T. So if X is greater than T, then X minus T plus, and this random variable is simply like X because of the memoryless property, right? So the expectation of X is simply 1 over lambda times this probability, which is a probability of X greater than T, and because X is exponential random variable, so probability of X greater than T is equal to exponential to the power of minus lambda T. Okay? And how about if X is less than or equal to T? And we know that if X is less than or equal to T, X minus T plus, this is simply 0. So we can just ignore this term. Now, we go back and look at expectation of minimum XT. Expectation of minimum XT is actually equal to expectation of X minus T plus. But of course, we have known that expectation of X minus T plus, right? So expectation of X is 1 over lambda. Expectation of X minus T plus is equal to 1 over lambda exponential to the power of minus lambda t. So it turns out that we can get expectation of the profit P will be S over lambda minus S over lambda exponential to the power of minus lambda t minus Ct. And then we can take derivative with respect to t of EP, and we plug in, and we solve for t, and we make it 0, and we solve for t. So t will be 1 over lambda log S over C. Now, if we ask a further question, if all unsold inventory can be returned for the amount R, and of course, this R must be less than minimum S and C. Otherwise, you can return all the commodities without selling any of them, right? So R must be less than minimum SC to make the question make sense. So, and there is a penalty cost P per pound of the unmet demand. So in this case, the expectation of profit would be like this. Previously, we know this like this, but now we add more complications. First, we have R, right? This is unsold. So unsold, the quantity of the unsold commodity must be T minus F. Recall that T is the order quantity, X is the demand. So T minus S will be the unsold, the quantity of unsold commodity. So T minus X plus, and you take expectation times the R. That is the price you can get back, right? Minus the penalty, that is X minus T plus, take expectation times penalty cost P. So again, we can use the equality minimum XT is T minus X plus. And remember that T minus X plus will be minimum XT minus T. We can move T to the left hand side, right? So that is, so if you take expectation, that would be, because T is not random, so it remains T minus expectation of minimum XT. And minimum XT, expectation of minimum XT have been solved previously, right? That is 1 over lambda minus 1 over lambda exponential minus lambda t. So we have this. And now we put everything back in this equality, and then we take derivative with respect to t and make it 0, and we can solve for t. And this is the optimal order quantity. And if you look at this optimal order quantity, and that is very obvious that if S increases, then T will increase. What does that mean? That means if S, what is S? S, recall that S is the price you can sell, right? So if you can sell the same commodity for more, then you should order more, and that really makes sense, right? And similarly, if R increases, T, the order quantity, also increases. Why is that? Because R is the price that you can get back for the unsold inventory. So if this R is large, then actually you are not afraid of ordering more commodity, right? So T will increase too. Hyper-exponential distribution. Let x1, x2 up to xn be independent exponential random variables with respective range lambda 1, lambda 2 up to lambda n. And if t, this t will be the independent of these random variables. And suppose that summation pj is equal to 1. And pj represents the probability that t is equal to j. Then we call xt a hyper-exponential random variable. So basically, you can think of xt as you randomly picking up a random variable from x1 to xn. And so this random variable xt, called hyper-exponential random variable, basically has two layers of randomness. One is from the t, because t can be 1 or 2 or 3 up to n, right? And the other is the randomness existing in x itself. So probability of x greater than t will be equal to the summation of the conditional probability x greater than t, conditioning on I is equal to I. So I can be 1 or 2 or 3 up to n, right? Times the probability t is equal to I. And probability of t is equal to I will be pi. And the condition on t is equal to I, the probability, conditional probability s greater than t will be exponential to the minus lambda it. So that will be 1 minus CDF f of t. So the PDF of t will be, we can just take the derivative with respect to t in here, right? 1 minus, and then you take derivative with respect to t. So we have the result like this. More about the exponential distribution. Suppose S1, S2 are independent exponential random variables with lambda 1 over lambda 1, 1 over lambda 2, which are their means. So their parameters are respectively lambda 1 and lambda 2. Then probability of S1 less than X2 will be probability of S1 less than X2 given that S1 is equal to X times the probability, the density that S1 is equal to X, which will be lambda 1 exponential minus lambda 1 X. And because now X1 is equal to X, so you can just replace X1 with little x here. So we have probability little x less than X2 times this. Then you take integration from 0 to infinity dx. And because X2 is actually an exponential random variable, so X2 greater than little x, this probability will be exponential minus lambda 2x times lambda 1 exponential minus lambda 1x, then integrate from 0 to infinity dx. Then it turns out that probability of x1 less than x2 will be lambda 1 over lambda 1 plus lambda 2. So from this result, you can see that if the random variable x1 has a higher raise lambda 1, then the probability that x1 less than x2 will be higher. On the other hand, if x1 has lower rate lambda 1, then the probability that x1 will be less than x2 will be lower. Let x1, x2 up to xn be independent exponential random variables with respective rates lambda 1 up to lambda n. Then the probability that xi will be the minimum of xj. Xj can be j can be 1, 2, 3 up to n. And that is equal to, because xi is the minimum, right? So that means xi less than minimum xj, j is not equal to I, because remember I is the minimum. And then that is equal to lambda I summation lambda j from 1 to n. Now we want to prove this. So suppose x1, x2 up to xn are independent exponential random variable having raised mu I. Then minimum of x1 to xn greater than x. And that means, because minimum is greater than x, that means all xi is greater than x for any I from 1 to n. And because all the xi are independent random variables, so this probability can be written as the multiplication of individual probability. And that is multiplication of exponential minus mu I times x. And then because this multiplication, we can move that and write that as exponential of minus summation mu I x. So that means minimum x1 to xn is actually exponentially distributed with parameter summation mu I. Example, suppose you arrive at the post office having two clerks. At the moment when both are busy, but there is no one else waiting in line, you will enter service when either clerk becomes free. If service times for clerk I are exponential with rate lambda I can be 1 or 2. Now we want to find the expectation of T, and T is the amount of time that you spend in the post office. So now, if we let Ri be the remaining service time of the customers with clerk I, so we have R1 and R2 because now we have two clerks. And by the lack of memory property, which is the memoryless property, R1 and R2 are both exponentially distributed with respective lambda 1, rate lambda 1 and lambda 2. So expectation of T can be written as expectation of T given that R1 is less than or equal to R2 times this probability plus expectation of T given R2 less than or equal to R1 times the probability. So this probability R1 less than or equal to R2 based on the property we just learned in previous slides, we know this is lambda 1 over lambda 1 plus lambda 2. And similarly, this probability is equal to lambda 2 over lambda 1 plus lambda 2. Now, we look at this expectation of T given that R1 less than R2. If T, that is the total amount of time you spend in the post office, if R1 is less than R2, that means the first clerk will finish the service before the second clerk, right? So basically, the total amount of time you spend in the post office will be R1 plus the service time the first clerk spent on you, right? So we can separate this R1 plus S. So we have expectation R1 given R1 less than R2 plus expectation of S given R1 less than R2. And R1 given R1 less than R2, and this is actually, the expectation is actually 1 over lambda 1 plus lambda 2. Why is that? We will see that very soon. And R1 less than R2, expectation of S given R1 less than R2, and this is, so that means the first clerk is going to service you. So basically the service time, the expectation of the service time will be 1 over lambda 1 like this. Now we look at why this is 1 over lambda 1 plus lambda 2. And because, okay, we finish this first. So similarly, expectation of T given R2 less than or equal to R1, and similarly, this will be 1 over lambda 1 plus lambda 2 plus 1 over lambda 2. So E of T comes to 3 over lambda 1 plus lambda 2. Now we look at why this is true. Note, so R1 given R1 less than R2, the expectation of R1 is actually equivalent to minimum R1 R2 given R1 less than R2. Because if R1 less than R2, R1 is the minimum, right? So that is equivalent to this. And now we want to prove that expectation of minimum R1 R2 given R1 less than R2 is exactly equal to expectation of minimum R1 R2. Why is that? Because minimum R1 R2 and R1 less than R2 are actually independent to each other. Now we prove that. So we have a property here. Our property states like what follows. So minimum xi and the rank ordering, for example, R1 less than R2 of the xi are actually independent. So we prove that. So probability of xi1 less than xi2 less than up to less than xin. So this represents the ordering. Given minimum xi greater than t, this conditional probability is equal to conditional probability that xi1 minus t less than xi2 minus t less than xin minus t, given that minimum xi greater than t. Why is that? Because if you minus t for every random variable, that does not affect the ordering at all, right? So this conditional probability will still be the same. And we know that if this is true, then this is actually equal to probability of xi1 less than xi2 less than xin. If we know, because knowing minimum xi greater than t or not does not affect this conditional probability at all. So that is equal to this probability. So in conclusion, we know that condition on R1 less than R2, R1 is the minimum of R1, R2 is exponential with rate lambda 1 plus lambda 2. So this explains why this expectation will be 1 over lambda 1 plus lambda 2. Another solution you can consider is like this. Expectation of t can be written as expectation of minimum R1, R2 plus s. And minimum R1, the expectation of minimum R1, R2 is 1 over lambda 1 plus lambda 2 per our previous slides, right? And plus expectation of s. And what is expectation of s? Expectation of s can be written as expectation of s given R1 less than R2 times the probability that R1 less than R2, which is lambda 1 over lambda 1 plus lambda 2, plus expectation of s given R2 less than or equal to R1 and times the probability that R2 is less than or equal to R1, which is lambda 2 over lambda 1 plus lambda 2. So totally that will become 2 over lambda 1 plus lambda 2. So if we put it back in here, we still get the same result, 3 over lambda 1 plus lambda 2.